So today we are doing section 8.3, vectors in the plane. The plane. Anybody know what that's from? Huh? I would be surprised, actually. Nice. It's actually an old TV show, Fantasy Island. Yes. And in the opening sequence, it's this island where you can go and live out your fantasies. And yeah, it was what's his name? Hervé something, I forget. But yeah, he'd be up at the top of the tower and he'd get all excited because the plane with the visitors for that week's episode came in, and he'd go, the plane, and it was a great show. They made a movie out of it, but I never saw it. But anyway, I digress. Let's talk about vectors in the plane. So some of you guys may have seen vectors before in your science classes, but I'm going to assume you haven't, so don't worry. So what is a vector? That is a great question. What is a vector? So geometrically speaking, we call it is a directed line segment. So what does that mean? Well, it means that it's a line segment, but with a direction. Sorry, just lost my mouse. Okay. So, for instance, maybe it starts right there at that point, and maybe it goes in this direction. Now you may be going, wait a minute, I thought you said it was a directed line segment. You just put an arrow at the end. What? Well, yes. Vectors have a direction, so you have to put an arrow to indicate the direction. But they do have a length. So we have an initial point. If I can spell initial point. Oh my God. But there actually is a point at the end of the arrowhead called a terminal point. So don't think of it like a ray in geometry. A vector is not a ray. In fact, I'm going to put that down here because that's important. A vector is not, sorry to yell, a ray. They look very similar when you draw them. But a ray has an infinite length, whereas a vector has a finite length. So a ray has no terminal point. It never ends. But why do we have these? So who cares? So it's a line segment that points in a direction. Well, who cares? Well, actually, vectors are really cool in physics. They have a whole lot of use. And so, I mean, they can describe all sorts of things in the real world. Think about, you're pushing on an object. You push on the object with a certain amount of force, and you're pushing in a certain direction. That force, the amount of force that you're pushing with, we can represent with a vector. And the length of the vector indicates the amount of force you're pushing with. So the more force, the more length this vector has. And then, of course, there's the direction. And so there's all sorts of things that we would use. I mean, I'm going to erase this so I wouldn't write it down if I were you guys. But like, let's say that you have this block and you're trying to pull it across a road. Like, you could pull in that direction with a certain amount of force. You could also, maybe there's multiple cables with multiple attach points. So maybe a cable is pulling from here and from here. What's the actual result going to be? And so the direction that you're pulling from makes a little bit of difference. Another thing kind of in the same the same vein, but think about a plane, and this is going to be our word problem that we have at the end. Maybe the plane is trying to fly in this direction. So it's flying with a certain speed, which is the length of the vector, and it's trying to fly in a certain direction, which is the direction of the vector. However, you have wind, and the wind is pushing it this way. The wind is pushing with a certain amount of speed. That would be the length of the vector for the wind. And of course, the wind is pushing in a certain direction. So what's the result? What direction does a plane actually end up flying in? And that's your resultant vector when you add the two vectors together. There's a whole lot of real world uses. We'll get a taste for it when we actually do our word problem, but we're going to talk a lot about vectors just kind of in the conceptual sense. Like I said, I'm gonna leave it up to your physics teacher whenever you take physics to get into the nitty-gritty of it. So anyway, let's talk about vectors. As far as notation goes, let's talk about notation real quick. So remember with when you have a ray, back in the good old days, I'm going to call that terminal point A. And then remember we'd put another point somewhere on the ray. The arrowhead, when you draw a ray, extends beyond that second point. And this is ray AB, or AB with the arrow on it. And that was a notation we used for arrays. It's very similar for vectors. So with vectors, I'll call the initial point C. One difference when you're drawing them is this second point, the terminal point, is right at the end of the arrowhead. So don't put it somewhere on the vector, because then you're drawing a ray. Put it at the very end of the arrowhead, and that's your terminal point. And so this is vector CD. Now you'll see it drawn in a couple of ways. If it's printed in a textbook, a lot of times you will just see CD, but they'll be in bold letters. But we can't really write in bold without, like, C, D. Okay, there's my bold C. What a pain in the butt that is. So we don't do that. Instead, we draw that. Now that's not a full-blown arrow. If you notice, it doesn't have like the bottom part. This is the symbol that's typically used. But again, it's one of those things you'll see people also just write this. I'm going to erase this, but you will see people write it like a ray with an arrow. I'm not going to, just because I want to make it clear we're talking about vectors. But it's there's like not a set standard, but this is probably one of the most common things. You can also use, it's standard when you're referring to a point to use capital letters, but you can also use a lowercase letter to represent a ray. And then we'll just put this. So vector CD, or U with a lowercase letter. All right, so let's see. Let's talk about component form of a vector. And chime in with any questions or anything that you got. Component form of a vector. So what does that mean? Well, like I said, vectors have length and they have direction. And so I'm just going to put one here and we'll talk about it. What is this actually saying? So vector U. I'm going to define vector U with a horizontal component of 3 and a vertical component of -2. And in vectors, we use these angle brackets. So I said it, but let me actually write it. The first number when you're doing component form, and by the way, actually, somebody brought up the XYZ plane and I ignored that, sorry. We're actually going to stay in just 2 dimensions in an XY plane, but this could be expanded to a 3rd dimension very easily. But that first component is your horizontal component. The second component is your vertical component. So what does that mean? Well, if I was going to draw vector u, its initial point could be anywhere. That's another nice thing about vectors, is we can actually place them anywhere that's convenient for the particular word problem. But when it says moving, when it says that we have a +3 for our horizontal component and a -2 for our vertical component, that means we're going to move 3 units vertically, 2 units negatively down, and there is my terminal point right there. That is my vector. I don't like how that looks. Oh, well, hang on, that sucks. Let me start over. Oh, I gotta learn this program. Okay, there's our initial point. There's our terminal point. There's our vector u. So we went 3 in the positive direction horizontally and 2 in the vertical direction negatively. And that tells us where to draw our vector u. Now you may be thinking, well, it's a lot like an x and a y coordinate, and you would not be wrong if you were thinking that. But don't think of it as an x and a y coordinate, because have I drawn axes? Nope. Now, we often put this on a plane, which I'm going to in a moment. So we often do draw it where we have an x and a y axis, but the point is you don't need it. And it can go anywhere on the plane. So I'm just drawing it there. And that's our vector u. So any questions about that? Okay. So then if I said something like this, if I just said draw vector v, which has a horizontal component of 4 and a vertical component of 6 on the coordinate plane. Okay, so now I'm going to put some axes down here. Let's see, black. And all right, so there's my perfectly straight lines. Nah. Okay, so if I'm going to put this on the coordinate plane, where do I start? That's my question. Well, the answer is anywhere you want to. So I could start here. And I could go 1, 2, 3, 4. I know you can't hear, actually, let me use this. 1, 2, 3, 4 horizontally, and 1, 2, 3, 4, 5, 6 vertically. And there's my terminal point. This could be vector v. Or maybe I felt like starting right here. Actually, I don't think I'll have room. Maybe I felt like starting right here. And then I could still do the same thing. I could go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and end up right there. I could put it anywhere. And depending on the problem, when you actually are using these in context, it may depend where you want to put it. Now, if you notice, let's say that I started at the origin, because that's probably where a lot of people were thinking of starting. It's a natural place. And then I go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and I could put it right there. You will notice that the coordinates for the terminal point end up being 4, 6. But it really, it really depends on the word problem, where you put the vectors. I mean, in a word problem, you're not usually just dealing with one vector. You're going to be combining multiple vectors in different ways. And so it really depends on the problem where you're going to put the vectors. So does that mean a vector could be horizontally and vertically shifted and it will still be the same vector? Oh my gosh, I love that question. Yes, it would still be the same vector. Let me say that again because this is perfect. Does that mean the vector could be horizontally and vertically shifted and it would still be the same vector? Yes. All three of these that I drew are the same vector. They're just in a different location on the plane, but they're all the same vector. Why wouldn't you start on the x-axis? I mean, just very loosely, when you're going to look, and we'll kind of get a taste of this in just a second when we talk about operations with vectors, but when you're looking at combining vectors together and you want to know the resultant force, like maybe you're pushing in one direction this way, but something else is pushing in a direction the other way, what direction is the object actually going to move in? So maybe you're pushing this way, but something else happens to be pushing this direction, then the result ends up being this way. So you can kind of do this head to tail business. I'll elaborate more on that in just a moment. But that's why you may not start at the origin. That's just one example. All right. Oh, let me put this down here. So a vector, we've talked about this, but we haven't actually written it down. A vector has a length which represents its magnitude. Now, I use the word magnitude. I mean, I've been talking about a force. We can use vectors to represent the force, and with the amount of force and the direction that it's going in, that could be a vector. But speed is also, velocity is a vector. We have the speed, which is the magnitude of the vector, but we have the direction that you're flying in or driving in or whatever it is, and that's the direction. So the magnitude, think of that as the amount of whatever it is you're talking about in the word problem, but it's represented by the length of the vector. So the more magnitude, the longer the vector is going to be. And then we have the direction, obviously. So a vector has a length which represents its magnitude, and it has a direction. So we're still just getting our feet wet in what a vector is. Any questions so far? All right. So let's talk about operations with vectors. Oh, actually, does anybody still need this? I'm going to go to a new page. Alrighty. Operations with vectors. Excuse me. So there's something called scalar multiplication. Multiplication. Whenever you hear the word scalar in math, it's a number. It's a constant. Scalar multiplication is very simple. Let's say I start with vector u, and I define it as having u1 for the horizontal component and u2 for the vertical component. u2. Sorry. And let's say that k is a constant. Then ku is ku1, ku2. Very simple. Looking at this geometrically with an actual example, let's check this out. So let's say that our vector u is -2, 1. Then 3u, you guys can probably figure out what that is right now. I probably could have just asked you, what do you think? If I said that u is -2, 1, what do you think 3u would be? You probably were already going to think of the right thing. Just multiply those numbers by 3. So it's going to be -6, 3. What? That's insane! I know, it's true. If we were to draw this out, see, -2, 1. I will start over. Whoops. If I just start with u right there and I go -2, 1, it will end up being that vector right there. That is vector u. What does vector 3u look like? Well, if I start over there and I go 1, 2, 3, 4, 5, 6, 1, 2, 3, then I'm right there. And you can see its length is 3 times as long as it was in the beginning. We've multiplied the magnitude by 3. What? That's all scalar multiplication is. But again, if you're going to increase the force, you can increase the magnitude. You're multiplying the vector by a scalar. Then we also have addition. Vector addition. And I've been kind of dancing around this, but again, like in word problems, it makes sense to combine our forces, to combine our vectors. And when we're combining them with a form of addition. We're combining them with vector addition. So what does vector addition look like? There's different ways to do it. You can do it geometrically, you can do it algebraically. We're going to look at both, and it really kind of depends on the circumstance which one you end up using. Usually you're kind of combining the two ideas together, but the geometric interpretation of vector addition looks like this. Actually, I'm going to do the algebraic first. Should have started with that. So let's say that I have vector u, and how about -3, 1? And then I have vector v, which is 2, -5. Now this is another one that I'll bet most of you could have just guessed and figured it out. Kind of go with your gut, so it's nice and intuitive. To add vector u plus v. Anybody want to take a guess what you think it is? Eh? Well, if you were thinking add the corresponding components together, you were correct. So, in other words, let's add the horizontal components together. -3 plus 2, that's -1. Add the vertical components together. 1 plus -5 is -4, and it's really that easy peasy lemon squeezy. So algebraic, very nice and simple. What does it look like geometrically? Well, I'm glad you asked. So the most common way of adding vectors geometrically, it's called the head to tail. And you just kind of stack them together. I'm going to, again, put it anywhere. It doesn't really matter where. I'm going to put vector u. So I want to make sure I have enough room. I'll put it down there. I'm sure that's going to be plenty of room. I'm going to go -3, 1. 1, 2, 3, 1. So there is my vector u. Now, to draw vector v, I started with vector u anywhere. But now what I want to do when I draw vector v is I'm going to start at where I ended for vector u. So I'm going to start at the terminal point for vector u. And I'm going to go 2, -5. So from this point, I'll go 1, 2, and then 1, 2, 3, 4, 5. Eek, come back here. So 1, 2, 1, 2, 3, 4, 5, and that is vector v. So what is the result? You can kind of think of it like this is taking the long way around, starting with u, you go there, and then you do v and you end up here. So now let's shorten the path. Where did you start originally, and where did you finally end at? And that's your result right there. So this right there is our vector u plus v. And if you take a look, it matches the components that we got when we added. What? Starting from here, if I go -1, -4, it matches. So that's the algebraic, that's the geometric interpretation. And so now I can explain sort of more. Somebody asked earlier, why would you not start at the origin? This is just one example. Maybe you did start at the origin for your one of your vectors, but when you place another vector, it makes more sense to place it where you ended the previous vector, because you're going to be adding the vectors together. So, yes. Mm-hmm. That's true, but the reason why I keep doing it in this way is just I'm doing it in the order the components come in with the when we write our vectors out, and you always put the horizontal component in first. So yeah, you could go down and then left, but still your left is the horizontal component, so that goes first. Does that answer your question? Okay, cool. All right. Any other questions so far? Okay. Oh, and then by the way, if you're thinking about, well, okay, so then what about subtraction? Subtraction can get weird geometrically. The easiest thing is just think of it as adding the opposite, like you first learned what subtraction was when you were doing integers. So for instance, if let's say that vector w, let's put a new letter in here, why not? Let's say vector w was 7, -2, and vector r is 3, 8. We're not going to draw it, we're just going to subtract them. Find w minus r. Now, the good news is, algebraically, okay, so you're going to subtract the components. Geometrically, though, think of it as adding the opposite. So, let me change colors here. So if we're going to do this, w minus r is the same thing as w plus -r. And then you're multiplying r by a scalar of -1. Actually, maybe we will draw this. So w was 7, -2. And then you're going to multiply r by a -1. So it's 7, -2 plus -3, -8. And then you can combine your corresponding components. So you're going to have 4, -10. I feel like I can't write as neatly. There, almost look like a -4. So that would be the vector right there, geometric or algebraically. And yes, if you were thinking, why did you do all that? Why didn't you just subtract? Why didn't you just go 7 minus 3 is 4, -2 minus 8 is -10, And the answer is just because I want to get across the geometric part. But you're right. If you just had to find the algebraic, just subtract. You're right. But if we're going to do it geometrically, then it makes more sense to think of it as adding the opposite. So 7, negative 2. I have no idea how much room. I should have made smaller numbers. I'm going to go right here. So I'm going to go 1, 2, 3, 4, 5, 6, 7, negative 2. There's my vector W. And then when I do the head to tail thing with vector R, I'm not going to draw R. I'm going to draw the opposite of R. So instead of drawing 3, 8, I'm going to draw negative 3, negative 8. So 1, 2, 3. Yeah, I'm gonna need, I planned badly, poorly. Should have thought ahead. Okay. So from the end, the terminal point of W, I'm going to go 1, 2, 3 in the negative direction. 1, 2, 3, 4, 5, 6, 7, 8 in the negative direction. So I'm drawing the opposite of R. 3, 4, 5, 6, 7, 8. So this is negative R. But then you can look at combining those, and this is W plus negative R, or W minus R. And then you can see it still matches. It still matches the 4, negative 10 that we got. All right, any questions about that? Alrighty then. Let's talk about this magnitude a little bit more. So magnitude of a vector. So let's say that I had vector t, and let's say that its components were 3, 4. Somebody wanted me to go up. So if we want, if I want to say the magnitude, first of all, there's some notation. So the notation for magnitude is it looks like an absolute value symbol, but it's doubled. So 2 bars on either side instead of 1 bar. And I'm just curious, without doing anything right now, based on what I've said, anybody have an idea what the magnitude of this vector is going to be? Let me give you a hint. I don't know if you remember, I said that the length of the vector is going to be equal to the magnitude. So can you figure out what the length of this vector would be? I see somebody put it in the chat. They put it privately, so not everybody saw. Oh, now I'm seeing a couple come through. Not privately. Yes, it would be 5. Does anybody want to share how you got 5? It's the Pythagorean Theorem. That's exactly it. Very nice. If I was going to draw a vector t, starting somewhere and then go to the right 3 units and then up 4 units, there's my vector t. We can see that we can easily make a right triangle out of this, and the length of the vector just ends up being the hypotenuse of it. So that's exactly where the formula for magnitude comes in, is from the Pythagorean theorem. So for our problem, a squared plus b squared would be 3 squared plus 4 squared But then you got to take the square root to find the length of the hypotenuse. So the formula for magnitude, if I just have vector u given by u1, oh, that's funny looking, u1, u2, then the magnitude of vector u is the square root of u1 squared plus u2 squared. And it comes from the Pythagorean Theorem. My 6th grade teacher used to say Pythagorean, which I just thought just was the silliest thing. Made me crack up every time she said. She had these really long nails too. She had these long nails that started to curl. And when she would write on the chalkboard, she'd had to hold the chalk like this. She'd had to go like this, hold it like this, so that her nails wouldn't touch the chalkboard. It's crazy. I don't know how she did anything. How do you put on your pants when you got nails like that? I've always wondered stuff like that. How do you do that? Anyway, the things that I think about. There you go. All right. Okay. Here's another idea that we do with vectors. Just trust that this has a use in real life when you're like using real world problems. Unit vectors. Unit vectors. Now remember, when we're talking in math and we say the word unit, don't think about anything dirty. Instead, what number should you be thinking about? Sorry, maybe that's old talk. I don't know. My mind's in the gutter. What can I say? What number should you think about, though, in math when you hear the word unit? Think about the unit circle. Yes, I see. One. Exactly. So when we talk about unit vectors, a unit vector is just simply a vector with a magnitude of 1. A vector with a magnitude of 1. So sometimes in our applications of these vectors, it makes sense to do something like I'm about to do, but it turns out that it's very easy to do, so that's good. So let's just look at a word problem, or I mean an example. Don't worry, no word problems yet. Find a unit vector in the direction of vector m, which we'll just say is at -2, 10. So how do we do that? It's actually pretty easy. So that we just use a simple formula. And the formula is, so the unit vector in the direction of m equals, I don't know why I made that capital. That should be lowercase m. We take the vector and we divide by its magnitude. It's very simple. So we have to find its magnitude, and then we divide the components, and you're done. So let's do that. Let's first find the magnitude. But we know how to find the magnitude because we have a formula up above, which is just the Pythagorean Theorem, so it's easy to remember. So we're going to do -2 squared plus 10 squared, all under a square root, which is going to be the square root of 104. But let's simplify this. 4 can go into 104 26 times. So it's going to be 2 root 26. So there's our magnitude. And then the unit vector, I won't write out all the words again, But the unit vector in the direction of m is, negative 2, 10 divided by the magnitude. So just imagine putting each of these components individually over 2 root 26. Negative 2 over 2 root 26 would be negative 1 over root 26, because we're also going to simplify. And then 10 over 2 root 26 would be 5 over root 26. And yeah, we're going to rationalize our denominators if we can, or if we need to. So this is going to be negative root 26 over 26, 5 root 26 over 26, and there's our answer. Da-da-da. So any questions about that? Alrighty. Now, it turns out that there's some special unit vectors. So let's talk about those. That is a unit vector right there. A unit vector, like I said, is any vector with a magnitude of 1. If you were to do the Pythagorean theorem on this, you're going to find it's got a magnitude of 1. But there's, like I said, there's some special unit vectors. They come in handy. Does anybody still need this first of all, though? Alrighty. Special unit vectors. So, we're only doing 2 dimensions, so we're only going to talk about 2 of them. But if we're going to be in 3 dimensions, there'd be 3 special unit vectors. Excuse me. One of them is vector I, lowercase I, and that is defined as 1, 0. And then vector j is 0, 1. By definition, that's what they are. Hopefully it's pretty obvious they're unit vectors, that the length of these is just going to be 1. If you only go 1 unit horizontally and that's it, you've gone 1 unit. Your length is 1. If you've only gone 1 unit vertically, you've only gone 1 unit. Your magnitude is 1. So why are these so important? Well, it actually gives us another way to write vectors, which ends up then also being really convenient to do operations with. Let's just take a look at this example. What if I wanted you to find 4i minus 3j? Find that vector in component form. Well, it's pretty easy. We know vector I is 1, 0, and we know vector j is 0, 1. So if we just replace I and j with their component forms, we get that. But we know how to do scalar multiplication with our vectors, and just like normal order of operations, we should do their multiplication first. So this first part becomes 4, 0. The second part becomes 0, 3. And then since I'm only caring about the algebraic part, I won't change it to the adding the opposite and do that whole thing. So now we'll just combine our corresponding components. 4 minus 0 gives us 4 for the horizontal component, and 0 minus 3 gives us negative 3 for the vertical component. And that is the resulting vector in component form. if you look at the original problem, could we have easily found those components without doing all that work? Why, yes. Our coefficients for I and j correspond to the horizontal and vertical components in component form. This is actually just another way to write a vector. So this, you'll hear, it does have a name. It's called linear combination form, because it's a linear combination of i's and j's. Some people call it IJ form. Component form is a technical word. Let's try to use that here. But this is one form of a vector. This is another form of a vector. And you'll see them both used pretty interchangeably. Sorry, I'm just peeking here. Okay. I think just one other idea and then we'll do a word problem. Yay. Any questions about that? All right. There is another form of a vector that's kind of weird. The one thing about this form, it's very handy. And again, when you're dealing in physics and you're dealing with actual applications of problems, it is very helpful often to know what the horizontal and the vertical components are. It's very helpful to take a force and break it down into just its horizontal component or just its vertical component. So this has a lot of use. However, I keep talking about how vectors also represent magnitude and direction, and that's what you can't see easily from here. What is the magnitude and the direction? Now, we talked about how to find the magnitude. We haven't really talked about how to find the direction yet, but then which we will, and then that gives us a third form for a vector, which is its direction and magnitude form. So let's just look at that. Now, like I said, we already talked about finding the magnitude, so let's talk about finding the direction of a vector. So if we're going to do that, now we are going to help us with this, we're going to take a vector and put it on the coordinate plane. And don't worry about, I have to turn that off. Don't worry about drawing like a specific, I'm just drawing a generic vector. This doesn't have a particular length or anything. Just generic. That's going to be our vector u. Now we know its length is the magnitude, but its direction we can define by this angle theta. So the good news is you can see now, oh, hey, this is going back to stuff we know with the unit circle, and it's going to bring us right back to the unit circle. If we say that this is our horizontal component and this is our vertical component, and if I define vector u as the components u1, u2, we can rewrite this in another way. So let's remind ourselves of something. First of all, for sake of this, I'm going to change the hypotenuse, because I want all of these labels to represent the length of the sides. So we know that the horizontal length is the same as the horizontal component. We know the vertical length is the same as a vertical component. I want the length of the hypotenuse then to be, in this case, it's the magnitude of the vector. So I'm just going to put those double bars to show it's the magnitude. But then, if we look at the cosine of theta, well, cosine of theta is the adjacent over the hypotenuse, or if I solve for u1, I can say u1 is the magnitude times cosine theta. And then I can do the exact same thing with sine. Sine of theta is the opposite over the magnitude. Opposite, there we go, over the magnitude. So U2 is the magnitude times sine of theta. And that should look familiar. So now what I'm going to do is I am going to replace U1 and U2 with what we just found they were equivalent to. U1 is the magnitude times cosine theta, and U2 is the magnitude times sine theta. So I am just taking this and replacing U1 with that, and I'm taking this, replacing U2 with that. But each component has a magnitude of U in it, so I can take that and factor it out. I can do like the reverse of scalar multiplication. And then it's just the magnitude times the vector defined by cosine theta sine theta. But we just saw up above that I can use I and j to represent this instead. So I can say that vector u is the magnitude times, and then the horizontal component is my coefficient for vector I. So it's cosine theta times I plus sine theta times j. So notice I switched from the angle brackets to the round brackets for this last line. And so this is another form of a vector. Honestly, I don't know if this one has a nice friendly name, but this form of the vector tells you the magnitude and direction. So let's end with a word problem. Where did I get I and j from again? So I'm using these vectors right here that were defined for us. So remember, I is 1, 0, j is 0, 1. But you can always see that your horizontal component is the coefficient for I, and then the vertical component becomes your coefficient for j. And so that's exactly what I did here. Horizontal component became the coefficient for I, vertical component became the coefficient for j. Okay, so let's look at a plane flying. I won't write down the whole word problem, just kind of abbreviate it. Won't make you write it all out. Time's a ticking. Does anybody still need this though? And your one word problem that you have for homework is very similar to this problem. So, okay, I'll read it all out, but then I'll just summarize it here. A plane is flying from Miami to Seattle. The plane's velocity with respect to the air is 580 miles per hour with a bearing of 332 degrees. The wind at the altitude of the plane is blowing from the southwest with a velocity of 60 miles per hour. And they were supposed to draw a diagram and write a velocity vector of the wind. So, what are we talking about here? So your plane, the plane is flying 580 miles per hour, a bearing of 332 degrees. The wind is blowing the plane. That's the basic idea here. The wind is blowing from, keyword there, from the southwest. And its velocity is, excuse me, stop it, at 60 miles per hour. So let's first just draw a diagram. And let's see how we do this. So let's draw the plane. So the plane is going at a bearing of 332 degrees. So if we think of that north line, we're going 90, 180, 270, 332. It's flying in this direction. That's the plane. And I'm going to just label this angle instead. So 332 minus, or from 360 is going to be 28 degrees. And let's call this vector P for plane. I'm going to draw this just a little bigger so I can label stuff. I want you to be able to read it. So that's 28 degrees. The key is that this is 580. Its speed is going to be the length of that. So that's 580. And anyway, that's the plane right there. Now, as far as the wind, so the wind is going from the southwest. So the southwest would be down here, and it's from that direction. So it's going in this direction. Now, where do you actually draw the wind? I don't really know. Do we draw the wind starting from the same place and going this direction? Should I draw it up here, going that direction? Because we're going to end up combining these vectors together, I haven't actually shown you what the final problem is going to be, but plane's going in one direction, wind's blowing in the other direction. Where is the plane actually going? We're going to want to add them. I'm going to put the wind up here. God. Sorry. I'm going to put the wind up here. And that's 60 miles per hour. Now the key is that's 45 degrees because it says from the southwest. So we're going to assume it's a perfect 45 degree angle. So there's our picture. And then for part B, if we write the velocity vector in component form, of the wind, here's what we need to do. We'll start with that magnitude and direction form. So the wind its magnitude, so I'm using this right up here. We're going to put the magnitude outside, and then we're going to put this form here. And you can put it in component form or in the linear combination. Since this says component form, I'm going to go back up here to the cosine theta sine theta. So we're going to have 60 cosine 45 degrees sine 45 degrees. And then, of course, you guys still remember your table of values. Cosine of 45 degrees is root 2 over 2. Sine of 45 degrees is also root 2 over 2. When we multiply through, we're going to get 30 root 2. 30 root 2. Dun, dun, dun. And then part C, we're going to do the same kind of thing. So let's do a velocity vector of the plane. But this is easy enough to do because it's going to be the magnitude times cosine of its bearing. And actually, we do have to be a little careful here. I don't want to do 332. We have to think of it as an angle in standard form, where we measure from the positive x-axis going counterclockwise. So 90 plus 28 is going to be 118. And just give me 1 extra minute. I'm sorry, guys. It won't take long. But there's our velocity vector. And if I'm going to go ahead and multiply it out. I'm going to do 580 times cosine of 118. And I'm getting negative 272.294. And then 580 times sine of 118, which is 512.109. And that makes sense in our picture. We're going negative and then positive. It seems to match the direction that our plane is actually going. So then for D, find the actual speed of the plane. Why do we do that? Oh, sorry. I didn't see that question until just now, so I don't know why do we do that. I don't know what that is referring to anymore. Sorry. If I call the wind vector W and I call the plane vector P, the actual speed of the plane is going to be the combination of the two vectors, but the magnitude of it. So it's going to be the magnitude of the plane vector plus the wind vector. But now we know how to do that. We can find P plus W just by adding those components together. 30 root 2 plus negative 272.294 is negative 229.867. And 30 root 2 plus 512.109 is 554.535. So then we can just do that Pythagorean theorem thing to find the vector, to find the magnitude. So if I can write this neater. Why do we measure cosine and sine? Oh, so it goes back to the unit circle thing again. So the question was about the 118. Why are we doing the 118 degrees? Because when we're going to actually calculate this, it has to be based on basically our unit circle idea of starting at the positive x-axis and going in the counterclockwise direction. So that's why. I'll finish working this out. If anybody wants to stick around, you can, but it's already 10:13. But hopefully you get the idea of once you have these numbers. But there you go. There's vectors in a nutshell. So there's your brief overview of vectors. So if you have questions, stick around. Otherwise, take off. Bye, guys. If you do the square root of the horizontal component squared plus the vertical component squared, you will get, ultimately, the plane is flying in about 600 miles per hour, which makes sense. The plane was going 580 miles per hour, but it does make sense with the direction that the wind is going, that it's going to help the plane out just a little bit. It's going to help, it's almost coming from behind to push it a little bit. Not a whole lot. So it makes sense that the plane doesn't increase by a whole lot, But it does make sense that the speed is increasing by just a little bit. So there you go. There's the end of the problem. Bye.